Hi there everybody. This is a video for my 40S pre-cal students, and I've been getting a lot of messages about the problems in the 8.4 applications of log functions. That's this assignment here, the second last one in the exercise booklet, and I'm getting kind of three different issues that they're popping up for people, so I'm going to try to address them all at once. First of all, I've had some people just straight up ask me, hey, do you have solutions instead of just an answer key? Not really, so I can make one right now, and I thought I'll just video myself making that solution guide so that you can kind of see my thought process and I can maybe explain them a little. The second thing that people are asking me is, they just, I'm not getting the same answers. And then I've had the third question is that people say, I just don't know how to start these problems. I don't quite know what they're asking me. I guess there's a fourth thing I've heard too. I had one person tell me that they understand the problems, but they're just having a really hard time understanding how to punch the buttons on their calculator. So I'll try to address all that at once. For those of you who are having trouble understanding some of the problems, it's not entirely your fault. I didn't realize, or I didn't remember until I was doing one with a student just this morning that, oh yeah, there's a couple on here that are actually really badly worded. So there's a story behind that. We'll tell you later why that is. Okay, I just want to make sure that this is recording properly. Okay, let's get into the questions here. So number one talks about a formula. I'll write it down, and it is the magnitude of an earthquake is equal to the log of the amplitude of the waves, which is measured in I don't know what that's measured in. I can't remember now. Some unit of force. Divided by kind of the reference amplitude. And I think the reference amplitude is, the fact of the matter is, the ground is never fully solid here on planet Earth. So there is kind of an acceptable baseline of sort of background movement that all tectonic plates around the Earth do, that they've considered the normal. And then earthquakes are measured compared to that normal. Anyway, that's the deal on this formula. Looking at the question here, and let's go through the questions here as we do. Now, in 2012, on February 1st, a spot on the edge. Okay, none of that matters. That's all nothing. What we want to do is look at what the question really wants from us. It wants us to figure out how many times bigger is a 7 earthquake than a 3.3 earthquake. And you might go, well, why can't I just use the 7 and the 3.3? Because the scale of M isn't in a linear step. It's the Richter scale is exponential. So basically, I have to compare the A values of the Manitoba earthquake versus the Haiti earthquake. And so I'm going to have to use this formula to get the A values so that I can compare them. Now, some people are having a hard time with this question because they were just stuck on, well, what do you mean how many times bigger? Just here, let me use scrap paper and just sort of give you an example here. Say, for example, we go back in time a year when I was 48 years old, and I had somebody in my grade 11 or 12 class that was 16 years old. How many times older am I than them? How do you figure that out? How do you represent that with a number? How do you figure out how many times something is bigger than something else? Well, you might go, well, wait a minute, this number, if I go times 3, right? 16 times 3 is 48. So the answer is that it's 3 times, my age is 3 times the student's age. So how do you find this 3? Well, you actually go 48 divided by 16. So what this question wants from me is, it really wants the amplitude of the Haitian earthquake divided by the amplitude of the Manitoba earthquake. So that's what I actually want to figure out here. Okay, and I'm actually, I guess I should put an A here because there's more than one part to this question. So for part A, I'm going to use that formula, and I'm going to find the ratio of AH divided by AM. So I can use this formula twice. I can use it for the Haitian earthquake, where the magnitude is 7, and 7 is equal to the log of the amplitude. And again, I'll say little h. Feel free to do that when you're doing math. Some people go, how did you know to put a little h there? Oh, I'm looking for the same variable but in 2 different situations. I don't want to make a whole new letter, so I'll just throw a subscript on it. So the amplitude of the Haitian earthquake divided by, again, that baseline measurement. What did they call it again? The reference amplitude. There we go. And that's for Haiti. And here in Manitoba, we have a 3.3. That's about the most this province has ever rocked when it comes to earthquakes, because I mean we are dead in the center of the biggest land plate in the whole world. So earthquakes don't happen too much here in Manitoba. In fact, again, 3.3 is, I think, the record. And so I'll say the amplitude of the Manitoba earthquake over the amplitude of the reference. So there we go. There's my two formulas. Now, what can I do with this? Well, there's a few things I can do. There's actually more than one way to approach these problems, but I always try to think about it in terms of what's maybe the easiest way to approach it. Remember that my log laws say that if I have the log of a divide, I can split that up into the log of a subtract. Right? And then I'll do the same thing for my Manitoba equation. Okay. Now, it doesn't tell me what this baseline amplitude is, but you know what I know is that it's the same in both equations. So I can actually say that if this number and this number are the same, why don't I rearrange the equation? So I'm going to move this to the left side by addition and then move the 7 to the other side. So the log of A naught is equal to the log of AH minus 7. And the log of A naught in this equation is equal to the log of the AM minus 3.3. And that means that I can compare this expression to this one because they both equal something that I know is the same, the reference magnitude. So I can compare them. The log of AH minus 7 equals the log of AM minus 3.3. Okay, so looking at that, I am going to basically rearrange this again so that I'm going to put the logs together. And I might as well put the constants together, so I'll add 7 to both sides. So that's going to be 7 minus 3.3. And then once again, I'll use my log laws. Remember, in my log laws, I know that a subtract is really a divide. So the log of AH over AM is equal to 7 minus 3.3, which is 3.7. And now I can actually change this into an exponential equation, right? Remember that this is a base 10. So the base 10 to the exponent 3.7 is equal to, and this was what I wanted, right? I wanted to know the ratio of the Haitian earthquake divided by the Manitoba earthquake. The same way that, again, I was 3 times older than that student because it's 48 divided by 16. So how many times bigger is it? Well, it's 10 to the 3.7. And I don't know what 10 to the 3.7 is, so I'm going to use my calculator for that. Let me put that up so that it can be seen. Let me just double check that I don't want the questions to go away, but oh, well, that's too high. You can't see that. There we go. Okay, there, you can see what I'm doing, I hope. So now I'm going to punch buttons here, and I'm going to say 10. And remember, your power button is right here, to the power of 3.7. And there we go. That's how you get the answer in the back. So therefore, this ratio is equal to, and you might as well round it to a whole number, 5,012 and times bigger. Or more, 5,012 times more powerful, if you'd rather say it that way. So that's how I'd solve 1A. Okay, so let's move on to 1B. Do that one. Okay, so let me see here. There we go. So 1B. And 1B is a similar one, the 2011 tsunami. Let's take a look at the question here. The 2011 tsunami in British Columbia, or sorry, in Japan was caused by an earthquake with a magnitude of 9. on British Columbia had one that was 6.3, and again, how many times more powerful? So it's really the exact same type of question. So let's approach it the same way. Okay, so here let's set up two equations. And remember, what I actually want is I would like to solve this for the amplitude of the Japan earthquake divided by the amplitude of the BC earthquake. That's my goal. I need to get to there, and I have two equations that can help me get there. I know that 9.0 is the magnitude when I have the log of the Japan earthquake, that's a J, over A naught, and I know that 6.3 is equal to the log of the BC earthquake divided by A naught, and I'll say BC, so that because I'm going to keep saying BC because it's in British Columbia. So there we go. There's my two equations, and I'm going to just approach this the same way. I'm going to turn this equation into a subtract. I'm trying to write neat because I'll post this so people can look at it too if they need to. And then I'm going to rearrange this for the log of AO. So, whoops. Don't lose the logarithm. Log of AO is equal to the log of Japan's minus 9. I can get rid of the 0.0. That's pointless. And same thing here. 6.3 is equal to the log of the BC amplitude minus the log of the, what do we call it again? The reference one, right? The reference amplitude. And again, rearranging it for that reference amplitude, the log of the reference amplitude is the log of the BC amplitude minus 6.3. This has to equal that because they both equal the same thing, the amplitude of the reference taken to the logarithm. Some people have asked me, when you get to here, why don't you just anti-log both sides? Well, you can't do that because of this constant, right? Same here, right? If you had, again, let me go to scrap paper. If you had an equation that was, you know, x squared equals x, or 2x squared equals x squared plus 3, hey, can't I just square root both sides of the equation and work with x? No, you can't. Two reasons, because you've got extra numbers here that won't allow you to do that. So, same problem here, because remember, logarithms are just the inverse of exponents, so they follow the same kind of rules as exponents. I can't just distribute an anti-log through that equation. So I can compare them though. The log of AJ is equal, or whoops, sorry, minus 9 is equal to the log of ABC minus 6.3. And then I'm going to collect my like terms, kind of. Then I'm going to change using my log laws that into a single logarithm, which is a divide. It's an A. Sorry, again, I'm trying to write nice and neat. And let's see, what is that? 9 plus 6.3. Oh, wait, sorry. Plus. That's a mistake. There's a minus there. I missed it. Minus. So that's going to be 2.7. So changing that now to an exponential equation, 10 to the power of 2.7 is going to actually equal the ratio that I wanted as my solution in the first place, right? This is what I wanted in the first place. How many times bigger is that than that? Well, I need to divide them to find that. And the division of those two things gives me 10 to the 2.7. Let me use the other calculator just in case you want a quick refresher on how that one works, right? Let's see, make sure, can you see me? Yep, good enough, okay. So let's see, that's 10, and that's the power of 2.7 equals, and there we go. So the answer is about 501 times, this is an earthquake, right? 501 times more powerful. 501 times more powerful. There we go. So there's 1A, there's 1B. Okay, 1C mixes it up a little bit. 1C wants you to think about it differently. In 1C, now we have an earthquake off the coast of Alaska, So the magnitude of an Alaskan earthquake is 6.4, and according to the formula then, that's going to equal the log of the amplitude of the Alaskan earthquake all over the reference magnitude. And we are also told that we know that, so let's see, let's go to the problem here. Let me look at the problem more closely. Problem. The magnitude of an earthquake off the coast of Alaska reached a 6.4, so I put that in. The one that hits Japan is 50 times more powerful. So it's not 50 times 6.4 because the scale for the Richter scale doesn't work that way. It's not linear, it's exponential. But the actual amplitudes can be compared that way. So the amplitude is 50 times more powerful. So armed with that knowledge, and let's see, does that actually work? Can you see the highlighting? Yeah, it looks like you can. Okay, good. So armed with the knowledge that that's the way it is, I basically can say that I know that the amplitude of the Japan earthquake is 50 times the amplitude of the Alaskan earthquake, which means that when I divide both sides by this one, this ratio, and I've been kind of solving for ratios all along, has to be 50, right? So keeping that in mind, I'm going to use this equation. I'm going to go 6.4 equals the log of A over A naught, okay? And basically, okay, I can say then that the magnitude of a Japan earthquake is going to be, and instead of writing down the amplitude of a Japan earthquake, well, I already have an expression for what the amplitude of a Japan earthquake can be. It's 50 times the Alaskan one, and then over A naught. And now I'm going to basically kind of solve these again, kind of the way I normally would. I'm just going to rearrange this a little bit. I'm going to say, all right, this equation has a number here already. And remember, this is a base of 10, so 10 to the power of 6.4 is equal to AA over A naught. And that means that this number here can replace this algebraically. So the magnitude of my Japan earthquake is going to be the log of 50 times 10 to the 6.4. Okay? Now, remember that everything after log here, until you hit an add or a subtract, is assumed to be kind of one argument. Remember the word argument? So you can do this more than one way. Here, I'll use this calculator first. And let me just double check that the calculator is still visible for you under the questions. Yeah, we're good. We're golden. So I can go 50 times 10 to the power of 6.4, get an answer for that, and then find the log of that, which is nice and easy. I just hit log, right? And there you go. You get about 8.1, which is their answer. If you have this kind of calculator, if you've got something more like this guy, you can actually do that all in one calculation. You can just go log and then open a bracket. And again, maybe I should double check that you can see what I'm doing. Well, maybe if I move down just a tad. There we go. So log of 50 times 10 to the power of 6.4, and then don't forget to close the bracket that tells the calculator that that's all the log there, and there you go, you get the same answer, 8.1. Okay. Keep in mind that if there is other ways you could approach this. I'm happy with just going with what my calculator does here. Oh, my screen froze. There we go. We're back. So that's about 8.1 on the Richter scale, and that's the answer that we get. Keep in mind, I could have done this an alternate way. I could have used my log laws. So, or alternate. And I could have just split this up into a plus. So I could have gone log of 50 and then plus. Now remember that when you take the log of 10, well, the log of 10 is 1. And remember that exponents in log laws can become coefficients. So really, the log of this is just 6.4 times 1. So that might be even easier button punching if you like. Let me go down a bit. You could just go log of 50 plus 6.4, and boom, there's your 8.1. So I don't really care which way you approach it. If you're really good with your log laws, this is less button punching, and kind of certainly in the days before these calculators were easily available, this is totally the way you would have solved it, because log 50 is something you could look up on a table. Nobody has a book of log tables that would list this number, whatever the heck it is. So this is the way you would have done it in the days before these things were on every desk. Okay, cool. So there's 1C. Moving along. Oy, this is going to be a long video. Number 2. But again, you don't have to watch the whole thing. You can just, watch me do some of it and then go back and try solving them yourself. And if you're stuck, you can just fast forward to wherever you need to go. So number 2. Number 2 is pH. pH is equal to the negative log of the hydroxide ion concentrations. Or hydrogen ion concentrations, I should say. And so that's what the pH scale is based on. It's a measurement of a concentration of a type of ion that you would find in a solution. And if you get a concentration that's a certain number, basically the pH of water, which is what we consider neutral, is considered 7. Anything smaller than 7 is an acid. Anything bigger than 7 is considered a base. Here we are with, let's look at me with my basic chemistry knowledge here. Just a humble math teacher. All right, let's see what we can do with that. 2A asks us to go the lactic. Oh, hang on. Let's roll the question into. Okay, there we go. There we go. Lactic acidosis is a disease characterized by excess lactate and a blood pH less than 3.75. Now, this number here is what you call a distractor, right? Am I asked to calculate anything involving this number? No, so ignore it. Some people are trying to do this problem going, what do I do with these two numbers? Actually, with this number, nothing. This is the number we're working with. Determine the concentration of hydrogen in that person. Which person is that? This person. The person severely affected by the disease. The 7.35, this entire first sentence is background story. 7.1 is the number we're working with, and this is a fairly straightforward question. It's just saying that we calculate the pH, or the H ion concentration. 7.1 is the pH, and we're asked to figure out what this concentration is. And if there's people in here who actually do chemistry, anybody doing any chemistry AP people and stuff especially, you're probably extremely unhappy that I'm just using a bracket. Here, I'll impress you even more with my chemistry knowledge. You're supposed to use square brackets when it's concentrations, regardless of the math involved. Haha, there we go. Now, what can we do here? The first thing we're going to do is we're going to multiply both sides or divide both sides of the equation by -1. I want the -1 away from my argument. Remember that negatives can't be part of the argument in a logarithm? And apparently I'm having a hard time spelling 3-letter words. Log. Eesh. There we go. There. I know that's a minor detail, but you're going to see that it's really important because the negative doesn't make sense anywhere else. It makes sense there. And now let's change this to an exponential equation. That's base 10. That's my exponent. And aha, see, the argument can't be negative, but the exponent can. And that's why we do it that way. So all I have to do now is actually punch buttons. And I'm glad that we're doing this because this gives us a chance to maybe talk about scientific notation a little bit, because I think the answer key gives you the answer in scientific notation. So here's what I'm going to do. On this calculator, I'm going to go 10 to the power of negative. Now, okay, I'm going to move up for a sec so you can see this. Remember, I'm using the negative button. Don't use subtract. You got to use the negative button. So 10 to the power of negative 7.1. Boom. And you get that. Now, that doesn't look like my answer. In fact, it's even rounded kind of different. How do you change a number on your screen to scientific notation? Well, actually on these calculators, it's kind of a pain in the butt. You have to go to setup on this brand, and I think some of them you can do it through mode. On Sharp's, mode is for other settings. It's not for scientific notation. You got to go to setup, and then FSE, and then go to scientific notation, and then there you go. And look at that, it even kind of still rounds it to 8 when it's really not 8. I'm actually not very pleased with that answer. So I have an alternate strategy. Oh, the other problem is now, of course, we're actually stuck in scientific notation, and we want to get out of it. So to get out of it, you go to, I think you go to setup. No, oh no, you don't. You go to mode, sorry. To get out of scientific notation, because again, notice you're stuck in it, you go to mode, and then you want to be in normal. And no, that didn't work either. Oh, I know what to do. Sorry. Here's what you do. You go to setup, you go to FSE, and then you go past, that's what you do. You go past all these guys. There you go. Now, this is what you want to do. Norm 1 and norm 2. Basically, it means normal way to display numbers 1 and 2. Actually, pick norm 2 if you have this kind of calculator, and you'll see why in a sec. Now I'm going to do that calculation again. 10 to the power of negative 7.1, and look at that. Ha! It gives you scientific notation. Basically now that you're in this mode, hey there, Mr. Lacko. Now that you're in this mode, I'll take care of that later. Okay. So now that I'm in this mode, basically anything that doesn't fit on the screen without showing you at least 3 or 4 decimal places, it'll just switch to scientific notation, which is kind of what we want. Most of these questions are going to want us to be at least 2 decimal places, right? So the answer is now something you can round to the way that it is. Does it say in the question where to round it to? No. So I'll round it to 2 decimal places. So that's 7 point, or actually 2 significant digits, which is what it is in the question. 7.9 times 10 to the negative 8. Okay. Now, how do you do any of that? And again, now what's nice is when it's just a simple decimal, it just gives me a simple decimal. But if it's a tougher decimal, like 1 divided by 9,000, it goes to scientific notation. And that's the advantage of being in mode normal 4 on these calculators. Haha, very cool. If you're on one of these guys, and again, let me just make sure that you can see me there. Good enough. I could even move up just a tad. Okay, there. If you're on one of these guys, to do this, of course, I think it's already kind of set up that you just do it the way we did it the second time. 10 to the power of, where's the power button? Power button of 7.1, and then make it negative. You have to type it in that order, and then hit equals, and there you go. Now, how do you change that to scientific notation if you want it? On this calculator, it is Shift 5. Can you see that? Shift 5, and there we go. Boom, you're in scientific notation. Why there isn't a nice quick shift like that on the other type of calculator and you have to actually change modes, I have no idea. I don't know why Sharp does that. Casios do that too sometimes, and it drives me crazy. But anyway, there you go. That's how you can do it. Okay. Even though it drives me crazy, I still like the way this works better. Doop. All right, so that's 2A. 2B is a little more complicated. For 2B, let's see, let's go to the question. It says, rain is said to be acidic if it has a pH less than 5.3. In some places in Ontario, rain can have a pH of 4.5. Again, those two things are just background information. Here's the question. Oh yeah, and this is one of the ones that got butchered. How often is rain with a pH of 4.5 acidic than normal rain at pH 5.6? And you're looking at that question going, ooh, first time with English. Yeah, actually what happened is this worksheet was originally in French, and when it got translated, it just got goofed up. What this question wants, instead of how often, it wants how many times more acidic is 4.5 than 5.6. And some of you, I think, already figured that out when you looked at this question. So please notice the wording here. How often rain with? Yeesh. What they're trying to ask you is how many times more acidic. How much more acidic, or how many times more acidic, which doesn't translate in French at all. How many times more acidic is the pH of 4.5 than normal rain of 5.6? By the way, notice that neutral water should be 7. So all rain is inherently, even when it's considered normal, is inherently acidic, and that's because rain is never pure water, right? So anyway, let's move along. Look at that. I'm teaching you some science too. Okay, so what do we want? We want the formula. pH equals the negative log of the hydrogen ion concentration. And, oh, and can you see that? I don't even know what you're looking at anymore. There we go, we're looking good. Okay, so you can see it. So let me just move up so it's a little more centered. And, okay, so what do we know? We know that we have 4.5 is equal to the negative log of the concentration of ions. And we'll call this A for my acidic rain, okay? And then move the negative to the other side. That's important, otherwise these don't work. And now change it to an exponential equation instead of a logarithmic equation. So the base of 10 exponent of negative 4.5 is equal to the HA concentration. Now once again, I'm being asked how many times more is one number than the other. So I'm going to actually want a ratio of the concentration of the acidic rain divided by the concentration of the normal rain. I'll put N for normal. Okay, but I now need an equation. I need this number for the normal rain. So for the normal rain, it said, what did it say, 5.6? So 5.6 is equal to the negative log of the concentration of HN ions. And move the negative to the other side. Negative 5.6 is equal to the log of HN ions. And okay, again, I'm in a log equation. I'm going to change it to an exponential one. So the base of 10 to the exponent 5.6 is equal to the HN concentration. So what I want for my answer is I want this as a ratio. So I want this number over that number. So HA over, can you still see that? Over HN, and those are both concentrations, is equal to 10 to the negative 4.5 divided by 10 to the negative 5.6. Okay, so there's my two numbers. And remember when you divide two exponents that have the same base, you can just subtract their exponents. So negative 4.5 minus negative 5.6 is like saying negative 4.5 plus 5.6. So that's actually 10 to the 1.1. And that I have to punch in my calculator because I don't know what that is. And so I don't know if you can see that. I might be too high. 10 to the power of 1.1. And boom, that's where they get their answer of 12.6 times more acidic. And there we go. So that's how they got 2B. Okay, so for 2C, let's take a look at 2C, shall we? And for 2C, they again make it a little more challenging. If the neutral water, if the pH of neutral water is 7, what is the pH of a solution 4 times, oh wait a minute, sorry, I'm on C. I'm getting ahead of myself, there's a D part. Michelle's conditioner is 100 times more acidic than her shampoo. The pH of the shampoo is 6.2. What is the pH of the conditioner? Okay, so for number 2C, I am going to say that the pH is equal to, again, the negative log of the hydrogen ion concentration. And the hydrogen ion concentration for the conditioner, put a little C for conditioner, is equal to 100 times the hydrogen ion concentration for the shampoo. I'll put a little S for shampoo. Okay, so still with me here? Let me just make sure everything's still lined up. Beautiful. Okay, so now, what do we know? We know that the pH of the shampoo, which can go right there in the formula, so the pH of the shampoo is 6.2. And that equals the negative log of the ion concentration of the shampoo, right? So I'm going to change that to an exponential equation. So 10, again, I'm moving the negative over. I'll do that in one step. So 10 to the negative 6.2 is equal to the concentration of HS. And I know that HS times 100 is equal to HC. So HC's concentration, the conditioner's concentration, is 100 times the number I just figured out. So 100 times 10 to the negative 6.2. Okay, and again, I can use my exponential laws here to make my calculation a little easier. That's basically 10 to the 2 times 10 to the negative 6.2. I can add those exponents, and that's 10 to the negative 4.2. And now that concentration can go into the formula to find the pH of the shampoo. So the pH of the shampoo is going to equal the negative log of the concentration. Why don't I just plug it in there? I don't need to rewrite the formula. Of 10 to the negative 4.2. And remember that in a log equation, a logarithmic equation, exponents become coefficients. So I have negative 1 times negative 4.2, which is just 4.2 times the log of 10. You should know this by now. What's log to the base 10 of 10? 1. So the final answer here is 4.2. And that's the pH of the shampoo. I'm pretty sure that's the answer they get. So that was 2C. All right, let's try 2D now. All right, let's look at 2D. 2D says, if neutral water has a pH of 7, what's the pH of a solution 4 times more basic? And then for some reason they put acid in brackets. I don't know why they're doing that or why they're saying that. But okay, whatever. Whatevs. How about we approach it this way? The pH of water is 7, and the pH of my base is what I'm looking for. And what I know is that the water is actually 4 times more acidic than the solution that's more basic. So I'm actually going to still times the 4 onto the water, right? So 4 times more acidic than this thing. Okay, so that's, oh, and I guess these need, I guess I should make chemists happy. Use concentration symbols. There we go. So there we go. That's what I'm told. There's my 2 givens. I'm given this, I'm given that, and I would like to figure out that. Okay, so the pH of water is equal to the negative log, and let me just again make sure that we're on here. There we go. Negative log of the concentration of hydrogen ions in the water. And so that number is 7. I'm going to move the negative to the other side. And I can rewrite that as 10 to the negative 7 equals the concentration of ions, like that. Okay, so now I know I can put this into that formula there and say then that the ion concentration of my base is 4 times 10 to the negative 7. Or I can just write that in scientific notation, 4 times 10 to the negative 7. So that's the concentration. Take that concentration and put it into a formula for the pH. So the pH of my base is going to equal the negative log of this number, 4 times 10 to the negative 7. And I'm at the point now where, again, I can do this kind of either way I want to do it. Let me just make sure you can see me. Yep, I can move up a little bit. Let's see, there we go. Okay, so once again, button punch tutorial here. You can, if you want to, just go, I'd like the negative of the log of, notice I'm just putting brackets inside of brackets, and you can actually enter 4 times 10 to the 7. You can actually punch that in as 4 and then hit your times button and then a 10 and then an exponent. Or are you aware that you can use your calculator to just do scientific notation? On this calculator it's called EXP. I don't know why scientific notation got the EXP. On the other calculator it's EE. But here, if you've never used your scientific notation button, check this out. It's actually really cool. 4, and this is my, I call it the times 10 to the button. Can you see what it does there? It makes a times 10 to the. Sorry if that's a little blurry. And then make sure you hit the negative sign for your negative 7, and don't hit the subtract sign. That would freak it out. Close the bracket for that, close the bracket for the log, and hit equals, and there you go. I think the final answer was the pH was 6.4. I'm pretty sure that was the right answer. I'm going to double check to make sure. Yep. So the pH was 6.4. Okay, let's do that on the other calculator just in case you wanted to do it. Okay, let's make sure. Oh, look at that. We're still in scientific notation. I'm going to want to get out of that. Okay, and on this calculator, to get out of scientific notation, just, let's see, there you go, turn it off and on, and let's see, are we still in scientific notation? 1 divided by 9, are we getting 0.1s? Yep, we're good. Okay, so, yeah, these calculators tend to not remember what mode you're in when you turn them off and on, so when you turn it off and on, you just go back to the standard mode. Anyway, how do I do this on that calculator? Well, okay, remember that you can't do something on this calculator to a number unless it's on the screen already. So I would like 4 times 10 to the, again, EE is my times 10 to the button, and then -7, and I want the log of that, and then I want to make it negative. And to make it negative, I'm just hitting the negative button. So, there we go, 6.4. Can I point out to you that once again, I could have done this a more alternative, more rule-using way. I could have said that that's the negative of log of 4 plus the log of 10 to the -7. And again, exponents become coefficients. So that's -7 times the log of 10, and the log of 10 is just 1. So this is the log of 4 minus 7, but then it's the negative of that. So again, if you didn't have access to one of these calculators, but you had a list of logs, and one of the things you could look up is this log of 4, and it would just tell you that the log of 4 is, you know, 0.602 blah blah blah. There you go. You can now just say that you know your answer is negative 0.602 minus 7. So take your number -7 and then get rid of the negative, and that gives you 6.4, which is the pH. Okay, so there's 2D. All right, number 3. Number 3, switching over to a much more fun science than chemistry. Sorry, chemistry people, but you're nowhere near as cool as astronomy. Astronomy, let me sharpen my pencil while I read this question. Astronomer Kepler discovered that log t equals 3/2 log d minus 6.23, where t is the time a planet takes to accomplish a revolution around the sun in Earth years, and d is its average distance from the sun in millions of kilometers. And then they go and they say nearest mile in a couple of questions. No, you don't have to convert kilometers to miles. I think that's just a typo. The answer key is in kilometers, so just pretend that says kilometers, okay? Anyway, Pluto is this many kilometers on the sun. I actually did have a student last year who thought this was a decimal, and that's why they didn't get the right answer, because they're, you know, they come from France or Italy or wherever they're from, where they use a comma instead of they use commas as decimals. They don't put commas in big numbers the way we do here in North America. So don't worry about that. That's just 5,906 million kilometers. This formula is in millions of kilometers. Notice the D is in millions of kilometers. So again, I had some people get this wrong because they slapped 6 zeros onto this and put it into the formula and wondered why it didn't work. Well, the formula is already built to use millions of kilometers. So let's get the formula out. So the formula is, this is number 3a, and I need log of t, which is the period to go around the sun measured in Earth years, of 3/2 of log of d, which is the distance from the sun in millions of kilometers. And there we have it. Okay, so this one's, the A one's actually fairly easy. We're just plugging numbers in. So the log of t for Pluto is 3/2 times the log, and the distance is again 5,906 minus 3.263. And again, I have people who go, oh, I can just anti-log both sides. No, you can't, because that constant is there. So you have to actually work this out. You actually have to take your calculator and punch buttons. So I'm gonna punch buttons here. Again, I hope that I'm on the screen. Let me do a quick check. Good enough. Okay, so 3/2, 3 divided by 2, times, notice it just changed that. If you wanted to use 1.5, that's fine. 5.906 logarithmed minus 3.263 equals And okay, so that is equal to, oh wait, that's not the right number. Hang on, something's gone wrong here. At least I think something's gone wrong. 3 divided by 2 times 5906 logged minus, yeah, there we go, 3.263. I must have punched something wrong the first time. There we go. That's the number I know I'm looking for. So the log of the period of Pluto's orbit is 2.39 blah, 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 blah. Now, I would like this to be as accurate as I can possibly get it, so I'm going to use this little trick. I am going to, and I'm going to move this up so you can see what buttons I'm pressing. I'm going to store this number in, let's see, store this number in memory 1. And now a little M1 comes up on the screen. And then I'm going to change this equation to exponential form. So 10 to the power of 2.39 blah, blah, blah is equal to the argument, TP, the period. And because I saved this number, I don't have to repunch decimals and be off. So I'm going to go 10 to the exponent, and then, can you see this? Recall 1, because that's where memory 1 is. And now it saved all that decimal, and it actually saved like a lot of places past this that it's not showing me on the screen. So I get a much more accurate number. So there we go. There's the number. Sorry. Can you see that? Let me just double check. Can you see? Oh, say, can you see? Yes, you can. Boom! And you get that the period is 247.7 years. I think they rounded to 248 in the answer key. Okay, guys who have different calculators, if you have one that works this way, and it's okay, it's like, but mine's a Casio, not a Sharp. The basic mechanics of this is always the same. So for this, I'm going to again get that number. So I'm going to go 3 halves times the log of 5906, close that bracket, and minus 3.263, and there's that number. And oh, once again, it's giving me oh yeah, you know what? Oh, it just put all of this in the denominator with the 2. I didn't want that. So open a bracket, 3 divided by 2, close the bracket. There we go. Haha. Times the log of 5906, and then minus 3.263. There we go. Sorry about that. Punch buttons. There's the number we want. Okay, now these kind of calculators have way down here, I'm sure I've pointed this out to you many times before, but they have an answer function on these calculators, which means that you don't need to use the memory like I did in the other calculator. You can just go here, and I'll leave this up high so you can see what I'm punching. I can just go 10 to the power of, and then notice how the answer's green, the alpha's green, and then alpha. And it puts, I know it just says answer, but it actually puts the last thing we calculated. It always, your answer button always tells you the last thing you calculated. And then that equals bada bing, 248 years. Okay, so that's A. B. Okay, let's look at B. Move that up. Let's go look at B. Mars has a period of revolution of 1.88. So now we're working backwards with the formula. And how far is Mars from the sun round to the nearest kilometer? What are we, Americans? I'll give you a little hint here. NASA doesn't work in miles either. If you ever go visit the JPL lab in Florida, they'll actually show you that you'll actually see the calculations on the wall on some of their work and stuff. They do everything metric there. Everything's metric because it's easier. It's a superior system in every way. Don't let anybody tell you different. Okay, so the log of okay, and I know T this time. I know that the period is 1.88 Earth years. So I'm going to put that there instead of the T. I might as well just go right to the number that I know T is, and that equals 3 halves of the log of the distance minus 3.263. Okay, what do we do with that? Well, what we're going to do with that is we're going to basically solve for D. So I have to isolate D. So I'm going to move this to the other side. So it's going to be the log of 1.88 plus 3.263. Then that is equal to 3/2 log d. Okay, how do you get rid of this? It's timesing the thing I'm trying to isolate. So I'm going to divide both sides by it. But when you divide by a fraction, remember that you can just times by its reciprocal. Oh, isn't that nice? Man, do I love algebra. Okay, we are ready to start solving this thing. I am going to get this into a number with my calculator. So let's see, and I honestly don't know if I'm on your screen or not here. Underneath the question. Yeah, that's good enough. Maybe move up just a tad. Beautiful. So, once again, do that in a bracket so it doesn't think all of this bracket is in the denominator with a 3. Open a bracket. 2/3 close brackets times, open the next bracket, the log of 1.88 plus 3.263, close the bracket, hidden equals, and there we go. 2.3581 is equal to log of d. So that means 10 to this power, 3581 blah blah blah, is equal to d. So d is equal to, and again, here's how I'm going to do this. I'm going to go 10 to the power of, and then I'm going down to that answer button again. So alpha answer equals, and there it is, 228 million kilometers. So why don't I just times that by a million? Because it did say it wanted the answer to the nearest mile. It meant kilometer. So that means it doesn't want me to round it there. So times by 1 million, right? So 1, 2, 3, 4, 5, 6, and there we go. And that would be 228,089,468 kilometers. And I think that's the answer key has, rounded to the nearest. Okay, cool. Now, how do I do that with this calculator? Let me run through that again for you. And again, if you don't have this kind of calculator, by all means, you can skip this part. But let me show you something. Remember that this still had something stuck in memory 1. If I'd like to clear that memory, what I do is I make sure 0 is on the screen, and then I store 0 in memory 1. So go to store, and then hit 1 for memory 1, and then notice the little memory 1 is gone now. It erases the memory when you save 0, basically is what happens. Okay, so 2/3 of times is of. My screen just froze on me. I'm moving too many things here. Anyway, I just hit times. Let me, I'll start over. Stupid screen. 2/3 of, open a bracket, 1.88 logarithm plus 3.263, close my brackets, and hit equals. There's that number. Store that in memory 1. I just hit a 1 off the screen there, and that's why the little M1 came up. You could, I think there's 3 memories in these things. You can store something in memory 1, memory 2, or memory 3. Then 10 to the power of, recall what was in memory 1. Boom, there's your answer. And again, we times it by a million. And there it is. Okay. Okay. 3, was there a C to part 3? Yes, there was. C3. C3 is find the distance from the Earth to the Sun. Oh yeah, I had people stuck on this one. This is a good one. It's like, hey, well, they don't give me any numbers. Guess what I know in this one? I know that T, remember in this formula, here, let me write the formula again. T is, or sorry, log T. Log T is 3/2 of log of D minus 3.263. Okay, so it's like, well, they don't give me any numbers. How can I solve for this when I don't know that? Actually, you do know that. Remember that T represents the period compared in Earth years. Well, so how many Earth years does it take the Earth to go around the Sun? 1. So this is log of 1. the people who are stuck on this now, I can almost hear them through the internet going, oh! Of course, that totally makes sense when you get it explained to you, right? So this you can do in your head. 10 to the power of what makes 1? The log of 1 is 0. So I'm going to add 6.23 to both sides, or sorry, 3.263 to both sides, 263, and that is equal to 3/2 log of d. And then I'm going to times by 2 and divide by 3, or times by 2/3, so I'm going to take my calculator and figure that out. So 3.263 times 2 divide 3 is 2.175 roughly. So the log of d is 2.175 and 3 blah blah blah. And again, I want to change that to an exponential equation. So 10 to this power equals d. So d is going to equal, store that in memory 1, 10 to the power of what was in memory 1, and there you have it, 149 million kilometers. So times that by a million, and you get the distance of 149,738,450 kilometers from the Earth to a sun. Just a short hop away. Okay, that was number 3. Number 4. Number 4 is, oh, we did ones like this in the notes, right? This is a sound intensity problem. So feel free to try this one. It's just like the notes. If you don't need to watch me do this, you can turn the video off. The sound level B in decimals is defined by the equation. So for number 4a, I'm going to start with the equation. Sound intensity is in decibels is 10 times the log of I over I naught. Now this time they give you the I naught. They tell you that the absolute lowest end threshold of human hearing is 10 to the negative 12. I believe that's what is that, watts of power per meter squared, and that's the minimum intensity a person can hear. Things like dog whistles are actually at a lower intensity than that. I think they're actually 10 to the negative 13 roughly, so they're a whole 10 times less powerful, but dogs can hear it. That's why dog whistles can be heard by dogs but not by people. And of course, you young people out there watching this video, teenagers, you can actually hear a wider range of sounds than us adults can, which is interesting. Especially if you're not like me and you've blown out your hearing by listening to too much loud music in your life. Don't do that. Anyway, sound intensity of a hairdryer is that. Determine the sound level. Okay, so I am going to go to the equation and say, okay, so my intensity in decibels is 10 times the log of, and the I is, let's see, so 0.000. I gotta make sure I count the zeros right. I'm bad for that. I'm bad for miscounting zeros in questions like this. 0.1. Okay, did I count that right? Let's look at the question again. Yeah, I did. Yay. And divided by 10 to the negative 12. Okay, now, how do you want to do this? You can punch that in your calculator. Your calculator is more than capable of handling that. But again, for those of us who like to do more thinking than button punching, because we trust our brains better than our clumsy fingers, remember that if you move this decimal over 1, 2, 3, 4, 5 places that way, you get 10 to the negative 5. And you can divide these things by subtracting the exponents. Negative 5 minus negative 12 is actually 10 to the 7. So take a look at this, guys. You could have done this question without a calculator. This could be something on a provincial exam that would be on the non-calculator section. And as long as you know your exponent rules, it's not that hard. So remember that in a log equation, exponents become coefficients. And remember that the log of 10 is 1. So 10 times 7 times 1 is 70 decibels. So there's 4a. Okay, I'm going to go to a different page because I think 4b is bigger. 4b. 4b is asking us to compare a Firetruck siren to a lawnmower. How often, and again, how often is the sound? How many more times louder is the Firetruck than the lawnmower? And again, you can't just compare their decibels, because it's not how many times bigger is 90 than 60, because the scale of decibels, by the way, that's supposed to be dB, not BB. Holy cow, who typed this mess? Anyway, you can't just figure out how many times bigger is 90 than 60, because the scale for decibels is not linear. It's an exponential scale. So I have to actually figure out the sound intensity level. I have to find I. So I have two. So what I want is, again, I want to know how many times bigger is the I of the Firetruck over the I of the lawnmower, right? This divided by that will tell me which one is bigger, or by how many factors is this bigger than that, by dividing them. Just like, again, back in that old example, if I'm 48 and you're 16, 48 divided by 16 is 3. I'm 3 times older than you. So this intensity divided by that one. So let's find those intensities. The formula, again, is beta, or fancy B, beta, is equal to 10 times the log of I over I naught. Okay, so I know that the decibels for the Firetruck. Let me sharpen my pencil here for a sec. Okay, so the decibels for the Firetruck is 118, right? So 118 is equal to 10 times the log of I of the Firetruck over 10 to the negative 12. And for the lawnmower, it is 90 decibels is equal to 10 times the log of the intensity of the lawnmower, L, over my threshold of human hearing. So I need to get a ratio of this number divided by that number. So I need to isolate for this number and isolate for that number. So I'm going to divide both sides by 10. Okay, then this whole thing is the argument. The base is 10, and the exponent's 11.8. Okay, and then I can multiply both sides by 10 to the negative 12, which means I add those exponents, which is 10 to the, what would that be? 10 to the, I'll just, let's see, 11.8 minus 12, wouldn't that be negative 0.2? I think that's right. I almost reached for a calculator for that. There we go. There's your IF. And now let's do this one. So 10 divided into 90 is 9. And that's the log of IL over 10 to the negative 12. And then this is going to be 9 times, 10 to the power of 9 is equal to IL over 10 to the negative 12. Okay, timesing both sides by this number is going to be 9 plus negative 12, which is actually negative 3. So IL is equal to 10 to the negative 3. And remember what we wanted. We wanted I of the Firetruck over I of the lawnmower. So I want I of the Firetruck over I of the lawnmower. 10 to the negative 0.2 divided by 10 to the negative 3. So that's negative 0.2 minus negative 0.3, which is 10 to the 0.3. Oh, yeah, that's right. 0.23. That's not a 0.3. That's what confused me. Negative 0.2 minus negative 3 is positive 2.8. And I don't know what 10 to the power of 2.8 is, so I finally have to grab a calculator. And 10 to the power of 2.8 is 631 times louder. Right on. So that's for B. Last one. And a Justin Bieber concert. Any believers out there? Okay, 4C. Let me sharpen my pencil again. All right, so Justin Bieber's concert is 300,000 times noisier than a normal 60 decibel conversation, what is the sound level of the concert? So once again, that's my formula. 10 times the log of I over I naught. And I know that the I for the Bieber concert is 300,000 times the I for a conversation. So I can say that the I of a conversation, doing a cross multiplier, dividing both sides by 300,000, is the Bieber concert divided by 300,000. And I'm just going to plug that in to what I know. I know that in the equation for a conversation, this B is 60. And instead of I for the conversation, I'll plug in what I for the conversation is. It's the I of the Bieber concert over 300,000, now divided by I naught, which again is 10 to the negative 12. So I've got myself kind of a compound fraction or a complex fraction here. So I don't like that. So I am going to actually remember that in fraction land, division is the same as multiplying by the reciprocal. Okay? And let's see. From there, I can say, all right, I'm going to divide both sides of the equation by 10. And from there, I'm going to get myself a exponential equation. So the 10 is the base, the 6 is the exponent, and then that is equal to IB over 300,000 times 10 to the negative 12. I think what I'm going to do is I'm going to times both sides of the equation by this denominator. So I have 300,000 times 10 to the negative 12 times 10 to the power of 6 equals IB, and do a little bit of work on that, and let's see, that's actually 300,000 times 10 to the negative 6. So let's see, so that means that IB is 300,000 times 10 to the negative 6. Well, that's like saying 300,000 divided by, remember that 10 to the negative 6 would be in the denominator 10 to the positive 6, and that's just a 1 with 1, 2, 3, 4, 5, 6 zeros. So zeros can cancel when you're dividing, because you're just dividing out tens. So it's actually 0.3. 0.3, okay, and, oops, sorry, I'm off the page, 0.3. And now I'm going to just plug that into the formula again. And the formula was, of course, just the original formula, but now I'm doing it for the Bieber concert. The sound intensity is 10 times the log of 0.3 over 10 to the negative 12. And feel free to just, let's see, you could figure that out by, you could just punch buttons and get this decimal and find the log of it. In fact, I'll just do that. Here, I'll use this calculator this time. Come back to me, calculator. There's not enough light in here for my calculator to work. If I turn on too many lights, though, my page gets like glowing. It gets so bad to read. Anyway, 0.3 divided by 10 to the exponent negative 12 is that number. I would like the log of that number using my answer function. And then I want to times it by 10. And then, boom, it's about 115. If you'd like to do it a little bit more, a charming method, you could go 10 times, and then remember that this would be the log of 0.3 minus the log to the base, to the 10 to the negative 12. And remember, the log of 10 is 1. The exponent becomes the coefficient. So B is actually 10, I should put this in a bracket, times the log of 0.3 plus 12, right? Because I'm minusing a negative. And you'll see here, I'll use this calculator for this one. So the 0.3 log plus 12, and then times 10. And there you go. 115 decibels for a Justin Bieber concert. Really not worth losing your hearing over that. So that's it. That's the homework that a lot of people were really saying they had a hard time with. If you actually watched this whole video, wow, congratulations. If you just used part of it and it helped you, I'm glad it helped. I'll post this answer key so you can, or solution guide, so you can look at it online. Thanks everybody. Bye-bye.